Good afternoon, children. Today we are discussing about a progressive wave or a traveling wave. A wave that travels from one point to another without any boundary restrictions. If there is no boundary restriction for a wave to travel from one place to another place, that is called a progressive wave or a traveling wave. So we need to discuss about such a progressive wave that travels from one place to another without any boundary restrictions. So let's consider the wave traveling in the x direction. For example, the wave is traveling in the x direction. So the particles will be vibrating, and the particles vibration is shown here as this is the direction of the wave propagation, and the particles move. For example, the particles move up and down. Let it be. So here y shows the displacement of the particles in the y direction and the upward direction, or it can be even downward direction also. So let y shows the displacement of the wave, and this wave has an amplitude which is the maximum displacement. This is the maximum displacement. This maximum displacement is shown as a. So with the time, as the time evolves, this amplitude of the wave, even though amplitude is fixed, the displacement changes here. For example, here this is the displacement, this height is the displacement, but here this is the displacement, and this displacement becomes a maximum at this point, and that is the amplitude. We use a sine curve. This is a sine curve in order to represent the wave. So its displacement at any time y is shown, can be shown with the help of a sine function. For example, we can write it as a sine theta, where a is the maximum displacement, and theta, how it comes is that's related to the phase of this wave. For example, here if the angle is 0, here I can mark the angle is 0. For that 0, the displacement y is also 0. For an angle of theta is 90 degree, we get y is equal to a. That is at this point. It means this will be corresponding to 0 angle, this will correspond to 90 degree, and this will corresponds to 180 degree. Again at 180 degree, again the wave displacement is 0. When it becomes 270, it becomes again maximum. 360, it comes here. Why this comes to 360 here is, this wave, if I take this half from here to here, if I take, and this half if I join here, this just I bend it back, I can draw like this. This is like a complete circle, and the angle here will be 360 degree. That's how we take this equation in the form of sine theta. So for an angle 0 and for the last angle 360, the height of this wave displacement is 0. So we get it as, for theta is equal to 90 degree or 360 degree or 180 degree, we get a 0 displacement, that is y is 0. For a 90 degree, we get the maximum. For 0 degree, 360 degree, 180 degree, we get it as 0 height. So y is 0, displacement is 0 for 0 degree, 180 degree, 360 degree. It is maximum, that is y is equal to a for 90 degree and 270 degree. So that's how this wave is represented. So I can write y is equal to a sine theta and represent the wave. And we have already told this angle theta is related to the angular velocity omega, as omega is theta by t. From this I can write theta is equal to omega into t, which will give you y is equal to a sine, instead of theta I can write omega t. y is equal to a sine omega t. Can be written like this. So a wave can be represented using the equation y is equal to a sine omega t, where y shows the displacement of the particle at any time t. Omega is the angular frequency, that is theta by t. Now one more thing to tell. This displacement, as I am able to express it with the help of sine theta, I call this as a simple harmonic motion. This is a simple harmonic motion. A simple harmonic motion means displacement y can be expressed as a function of sine theta or can be cos theta. So such waves, if I can represent their displacement with the help of sine theta or cos theta, I call it as a simple harmonic motion. So this is an example of a simple harmonic motion. Now one more thing, let us take the displacement of the particle once again. So displacement, let's compare the displacement of the particle at O here, and let's compare it with the displacement of the particle at somewhere here at this place. You can take 2 points, one is here, one is here. Let's compare the displacement of the particle at these 2 points. So displacement of the particle at O, this point O, is this much distance behind that of P. So from P, this displacement is x behind at O. So that representation we will give with the help of, that we will show with the help of a term called phase. And that phase is represented as phi. This phi is a term showing how behind is the particle, the vibration of the, or the displacement of the particle, how behind it compared to the origin. So sometimes it can be even in the forward direction. So what to including this phi, we say the displacement y is equal to a sine omega t, already there it was there, plus or minus phi. That means some angle, it will be an angle, it will be some angle behind the particle or above the particle. So that's why we put a plus or minus symbol for phi. So in this special case, as the displacement of the particle at P is x behind, we can write y is equal to a sine omega t minus phi. As it is behind, the displacement of the particle at O is behind that the particle at P, we can write y is equal to a sine omega t minus phi. And let's try to look at this phi again once again. I told the phi is the angle showing the displacement of the particle. So for a wave, this for one full wave, that is, if you take one full wavelength, suppose if this is one wave, one full wave, I told this I can this lower half I can bring it down, this part alone I can join back here. That means full wave is shown by a wavelength. One full wave, its length is equivalent to an angle of 360 degree or 2 pi. 2 pi. So in that sense, what we do is we express this phi, this phase difference term, the angle term, as 2 pi by lambda times x. So there is an equation representing this phi. 2 pi by lambda x is phi. So in that sense, we can substitute this equation phi as a sine omega t minus, instead of phi we can give 2 pi by lambda x. And one more term, we had a term called omega, that was, we told it's omega theta by t, it can be expressed as 2 pi by t also. We had an equation like that, 2 pi by t. So if you substitute that we get y is equal to a sine omega, that is 2 pi by t into small t. Omega t was there, a sine omega t minus phi. Just now we told 2 pi by x, lambda into x is phi. So from this equation, if you take 2 pi by t outside, we get y equal to a sine 2 pi by t into t minus, there is no t in this equation. In the second part there is no t, so we give a t in the numerator, so that when I multiply this 2 pi by t inside, this t and t will cancel. You will get 2 pi by lambda into x. So this is one way of representing the wave y is equal to a sine 2 pi by t minus x. And now there is a t by lambda, t divided by lambda, that is the time period by wavelength. This is nothing but the velocity of the wave. So this t by lambda is nothing but the 1 by velocity. This is coming from the equation v is equal to lambda by t. How this is v is equal to lambda t by t is, we know v is the speed, and that can be expressed as a distance by time. So for one wave, the distance is known as wavelength, and its time is, corresponding time is time period. For one single wave you take, if you take this much distance, this is the distance, that is wavelength lambda by the time for one wave is called a time period, so capital T. So if that also we can consider, then we can get the equation v is, y is equal to a sine 2 pi by t, t minus x by v. In this way also we can express this wave equation. So all these equations are representing the wave.